Module 12, the definite integral. Previously, we had been studying the antiderivatives, or in other words, the indefinite integrals. Now, what's the difference between the two, the definite versus the indefinite integrals? The antiderivatives are called indefinite integral because they are not unique. That's because of the integral constant plus c, which disappears when you take the derivative. Consequently, there are infinitely many antiderivatives, or with some pun intended, indefinitely many. The definite integral, on the other hand, is uniquely determined for a given continuous function in a closed and bounded interval a and b. Here's a graphical representation. Please take a look at this graph, y equals f of x. It's a continuous function, as you can see, and starting from 0 to 3.5, and that's the interval a to b. We're going to have some color coding here to enhance our understanding. When the function value is positive, in other words, the graph is above the x-axis, we're going to put blue, and red represents when the function value is negative. We're going to put minus sign to red area and plus sign for blue area, and we're going to add them all up. If there are more than one red and more than one blue areas, add them all up. That signed area is called the definite integral. More precisely speaking, I shouldn't be saying is called. The precise definition of the definite integral will be made in Module 14 and revisited in Calc 2. I should have said that is the geometrical representation of the definite integral. The definite integral as the signed area. Another way to regard the definite integral is through the concept of accumulation. Here's an analogy. Let's consider this graph represents the daily profit of your business venture. For example, looks like first 1 year or so, you had been losing money in your business, so daily profit is negative for a little bit more than 1 year. And then after that, it is taking off, and then you're making profit. Now here's a question. What is your accumulated profit from day 0 to current situation 3.5 years later? Entire accumulation, all the loss, and then profit put together. That is the signed area, and that is the definite integral. In this particular case, blue region is bigger, so your business had been doing good. Accumulated profit is positive. It could go the other way around when red region is bigger. Now let's go to the notation issue, and that's important. We talked about those in the previous module when we discussed in the indefinite integral. Here we go. The integral a to b, which represents the starting point of the integral, also it gives you the starting and ending point of the interval, followed by the function f of x, which we call the integrand, and finally the closure dx. All three are important components of the definite integral notation. The same grading scale will apply. Misusing or misplacing the integral sign up to 2 points off. Misusing or missing dx 1 point off for each mistake. Now that we talked about the meaning of the definite integral, let's talk about some of the properties. There are these 3 properties intrinsic to the definite integral, and then there are 2 more properties which are shared by both definite and indefinite integrals. These first. The integral from a to a f of x dx is 0. No matter what function we have, if we start and end at the same point, the signed area is 0. Here is a visualization. We do not have an interval because starting and ending point is the same. So what do we get? We have line segment, and the area of the line segment, of course, that's 0. Next, integral from a to b and integral from b to c put together, we get integral from a to c. We can join them together. Here's a visualization. Integral from a to b is brown. Here's a, and then going to b. And integral from b to c, that's purple. Add them together, what do we get? We have to get the entire accumulation from a all the way up to c. It's easy to see. Next, this one is a little bit difficult to understand and requires some thinking. One way to understand it is go back to the signed area concept. And positive y-coordinate value going up, that's plus. Negative y-coordinate value, that's going down. So up or down represented plus, minus, respectively. And that's for the y-coordinate, the function value. How about the x-coordinate then? Going to the right is plus, going to the left is negative. Now, look at this. From b to a, that's going backward, versus a to b. And that's why we have negative. This one is going backward, going to the left. A to b, that's going to the right. So we need this minus sign. That's one way to understand this phenomena. Another way to see it, okay, this is going to be a little bit harder, but it's more accurate. We're going to use the second property there, where we're going to put b to a, and then again a to b. So put those together using the second property. What do you get? We get the integral from b to b. And then we can apply the first rule. Starting and ending point of the integral is the same, so what do you get? This is 0. Consequently, integral from b to a plus integral from a to b is equal to 0. So all you have to do is flip this to the other side. And what do we get? We get desired identity. Now, if this is a little bit too hard, then you can regard this one as just a formula. But my expectation is everybody should be able to understand this when he or she sees it. Okay? I'm not saying everybody should be able to reproduce this out of scratch, but if you see it, you should be able to understand it, both graphically and also algebraically. Now let's go over to the next properties, and these are easier because the same properties are shared with indefinite integrals and also the derivatives. You can multiply by constant k, the coefficient, either before or after taking the derivative, antiderivative, or integral. And same for the addition. You can add before or after taking the derivative, antiderivative, or the integral. Now, as for the addition, there are two aspects. You can decompose addition of two functions, or you can decompose addition of two intervals. There are two aspects. Now, one more concept, and then we're going to do some application problem here. And okay, the average value. I admit this is not as important as the others as far as math course is concerned, but in some other course, this is important. Physics, chemistry, engineering, business, you name it. The average of certain function in a certain time frame or any kind of interval means something. In math, however, it's just a formula. The integral from a to b f of x dx, yeah, okay, we'll have to calculate this, but assuming you did that, all you have to do is multiply by 1 over b minus a. So it's a formula. It's just a simple computation once you complete calculating the definite integral. For that reason, I don't really like this average value problem very much, and I haven't written it in the exam for a really long time. But in other discipline, they mean something. Now, finally, there's a visualization of this average concept, and it's here. This average is actually the y-coordinate of this black horizontal line here. And this integral is a signed area of this entire graph, red and blue put together. And what does this average value do? the area underneath this black line. So this area of this rectangle where I'm running my mouse around, this area of this rectangle is the same as the signed area of this entire integral. Now blue part is bigger, so this average is positive, so we have something like this. But if red part had been bigger, then black line will go down below, and then the average will be negative. Okay, so much for the properties and then the meaning of the definite integral. Remember all these. Now let's go over to some application, and let's begin with some estimation problem. Not the precise computation, but some estimation. Here's a graph, and then let's find out an estimated value of this integral 0 to 3 f of x dx. As usual, we're going to assume each grid count for 1 unit, and here's 0, the origin, and x equals 3 is over here. And then in this interval, graph is down below, so this integral value will be negative. And then if we make further estimation, it goes like this: 1, 2, 3, 4, 5 squares are completely enclosed, and then I'll be more. Wait a minute, there's a better picture here. Okay, here. 5 squares are completely enclosed, and then half, and then I'll be more. So I estimate something like negative 6.2, just an estimation. And the precise computation using Mathematica yielded this kind of computation. So that rough estimation was pretty good. Even if your rough estimation is wildly wrong, I'll still give you full credit. If you write something like negative 6.7 or negative 6.9, negative 5.8, I'll still give you full credit. Now, if you write something like negative 4 point something, that's not good because it's clear that there are 5 squares completely enclosed. So your value should be negative 5.5 to negative 6 point something clearly. So if you go beyond that window, I may take off some point. And of course, another important thing is the negative here. You see, the graph goes below the x-axis, so overall, the signed area has to be negative. Here's another estimation problem. Integral 3 to 6 f of x dx, where's 3 right over here, and then 4, and then 5, 6, some negative part, some positive part, so you'll have to do something like this. Some red, some blue, add them together. Okay, let's do some shading. Here is better picture. 3 to 4, so here's some red part, and 4 to 6, some green part, adding them together. And this is just an estimation, so I'm using triangles for estimation. And this one goes a little bit less than negative 2, but still I just estimate it as negative 2 as a height. And this is the signed area for the red part, negative. And this is the signed area for the green part, positive. Calculate, I got something like 4.0 approximately, of course. And the real computation is 4.23 something. Again, pretty good estimation.